Okay, let's push on with our little chat about the theory of flight. Now what we're going to start off with is the standard atmosphere. We'll have a chat about that. Then we'll move on to aircraft geometry, nomenclature, how we describe an aircraft. We'll then look at the balance of forces in gliding flight, steady gliding flight, and then the generation of lift, gliding performance. And when we're looking at gliding performance, it's important that we know how we create drag on the aircraft, or more accurately how we try and reduce the drag of the aircraft. Then we'll move on to stability and control, how we can make sure that our aircraft is safe to fly. And we'll look at turning flight, a little bit of importance there because our stall speed is dependent on the G that we're pulling, so we'll have a look at that and we'll see how the G we're pulling changes during turning flight and how that affects the stall speed. And because of that, we'll look at the flight envelope. There are restrictions on how fast we can fly the aircraft, how fast we can fly the aircraft in various different atmospheric conditions. Look at it there. Once we've done that, we'll then move on to another set of lectures where we'll look at flight instruments. So the first thing we're going to look at is the atmosphere. And the atmosphere is really defined by the International Standard Atmosphere, or ISA. The International Standard Atmosphere is essentially kind of an average atmosphere. It's what the atmosphere generally looks like on a day-to-day basis in temperate climates. It's not true that our atmosphere actually looks like this, because the atmosphere will change day to day. But it gives us an idea about what the atmosphere looks like on an average day, and it allows aircraft designers to calculate the performance of their aircraft based on a standard atmosphere. Now, the aerodynamic performance of our aircraft will depend on the properties of the air as it goes up through the atmosphere, particularly the pressure, the density and the temperature, and that's what our standard atmosphere tells us. And we also use the International Standard Atmosphere to calibrate our flight instruments, such as the airspeed indicator and the altimeter. Now that's what our International Standard Atmosphere looks like, and it breaks up the atmosphere into 3 zones when we're close to the Earth, and these are the ones that really affect us. There are some other areas which are outside the atmosphere or on the margins of space. Where we live, here's what's known as the troposphere. Now the troposphere is the region of the atmosphere between sea level up to about 11 kilometers, about 33,000 feet. And inside the troposphere, what we find is that the temperature decreases linearly with height, all the way up to 33,000 feet, 11 kilometers. And once we pass what's known as the tropopause, then the temperature remains constant at minus 56.5 degrees C. And that area where the temperature remains constant is referred to as the stratosphere. Once we reach the edge of the stratosphere, we enter the mesosphere, where the temperature starts rising again. But that's up at about 70,000 feet. So most of the time we live down here in the troposphere, and we fly mostly in the troposphere. We might, on a very, very, very good wave day, get up to the tropopause and a little bit maybe in the stratosphere if you're very lucky. Most jet aircraft, when we're going on holiday in our 737, 777, we're flying up in the stratosphere, down with very cold temperatures. So you're sipping your martini in a nice 20 degrees cabin, but outside it's below minus 50 degrees C. There's very few aircraft that fly up in the mesosphere. We're talking there about the SR-71, the Blackbird when it was flying, and the U-2 spy plane. I think they're still going. And if you look, there is something called the Perlin project where they're trying to fly in wave up to the edge of the stratosphere and the edge of the mesosphere in a suitably adapted glider in wave down the Andes. But there's our international standard atmosphere, showing us how the temperature changes with altitude on an average day. Now that lapse rate, or the way that the temperature decreases with height in the troposphere, that's referred to as the dry adiabatic lapse rate, and it's 6.5 degrees C per kilometre. What does adiabatic mean? That means no heat transfer. And where do we get heat transfer from? Well, if we have an atmosphere that is moist, what can happen is that moisture can condense and evaporate and therefore take heat from and to the air, and that will change the way that the temperature varies with height. But this constant temperature is known as the dry adiabatic lapse rate and assumes no heat transfer to the air as it rises. Now, what's the standard sea level values for the International Standard Atmosphere? And these are set. And the ISA sea level values are 101.3 kilonewtons per square metre, or kilopascals, and in old terms that's 1013 millibar. Now, once we start going above what's known as the transition altitude when we're flying, we need to turn our altimeter onto what's known as the standard altimeter setting, or the standard pressure setting, because then we can fly at flight levels. And if we look at the standard half-million map, we will see that Class A airspace in the air corridors is given, or the bases and tops are given in flight levels, and flight levels are relative to 1013 millibar, and that's why we use that pressure setting. It's ISA sea level value. The density at sea level in ISA conditions is 1.225 kilograms per cubic metre. And when we look at flight instruments a little bit later on, we'll talk about what's known as indicated airspeed, where our airspeed indicator is calibrated with a density of 1.225 kilograms per cubic metre. And it's because it's ISA sea level density. If we look at the temperature, sea level ISA day, that's 15 degrees C. Density and pressure also change as we go up through the atmosphere. Pressure varies almost linearly as we go up through the atmosphere, and that's how we essentially calibrate our altimeter. Our altimeter is just a posh pressure measuring device which is calibrated for the pressure it measures, the static pressure it measures, and then it indicates the altitude we're at. Density, again, varies linearly as we go up through the atmosphere, and we can see that our density drops quite quickly as we go from sea level, 1.225, up to 6,000 feet. We're down to 1 kilogram per cubic metre. So around about 10% drop in density as we go up through 3,000 feet at 1,000 metres. So if you ever wonder why you're on tow behind the Eurofox, which has a naturally aspirated engine, and it seems to take forever to get up to 4,000 or 5,000 feet, well, if we look here, we can see that our density, and therefore the amount of kind of air that's getting into the cylinder head as we combust the fuel air mixture, has dropped by 10% by the time we get up to 3,000 feet, and will have dropped to by about 20% when we get up to 6,000 feet, and therefore the power that we're getting out of the engine will have also have dropped by about 10% at 3,000 feet and 20% at 6,000 feet. So it's important we know how the density changes as we go up through the atmosphere. Now that's the International Standard Atmosphere, and it's a rough idea of how the atmosphere behaves on an average day. In real life, our atmosphere is moist and there is water vapor, and therefore the air is humid, and depending on the amount of water vapor that exists within the atmosphere, then the density will also change. And so our actual atmosphere doesn't behave like the International Standard Atmosphere. It's slightly different. But what we do see is that temperature changes with height. And this is what's known as a tephigram. which shows us the variation. In this case it's from RASP, so it's a forecasted value. It shows us how the temperature is forecast to change with height, and we see that it doesn't exactly follow what the International Standard Atmosphere says. It's different. What we also see on the tephogram is the dew point, and the temperature at which moisture in the atmosphere will start to condense out. On the left here, what we can see is where there is predicted to be cloud, and what we see is once the temperature of the air reaches the dew point, water vapor condenses out, and we can see that there is cloud predicted. Now, tephograms, reading tephograms, there's loads of great videos on YouTube. Have a look at them, see how you read tephograms, gives you more information about the atmosphere. But suffice to say that in general, temperature drops with height in the troposphere, remains constant in the stratosphere. The pressure decreases almost linearly with height, as does the density. Well, there we go. That's a quick look at what we would expect to see with our atmosphere.